So last time we studied CR equations, and they said that if f of z is equal to u of xy plus iv of xy, then CR equation means those CR relations were written as del u by del v, del u by del x is equal to del v by del y, and del u by del y is equal to minus del v by del x. So these were the two CR relations for this condition. But here we have taken Cartesian coordinates. There is one more relation available for polar coordinates. So there are CR relation in polar form also. So let us write that down. That is also useful sometimes. So they are called CR equations for polar coordinates, or they are also called polar form of CR equation. CR means Cauchy-Riemann equations, right? So there is this you can write it like polar form of CR equations, and it is like this, that del u, so polar coordinates are r and theta. Okay, so we will write the CR relations in terms of r and theta instead of x and y. So del u by del r, just like we had del u by del x, had some relation with y. Of course, the derivative of v with respect to y. Similarly, we will have del u by del r, and then we will have del v in terms of del theta, but then there is 1 over r here. And then just like that, del v by del r is equal to minus 1 by r del u by del theta. So these two are the CR equations for polar coordinates, and yes, the thing we'll see later on. So this is it. These are the polar form of CR equation. You should note this down. Sometimes they are helpful in solving some problems. Okay. After seeing this, we will study one more little topic, and that is called harmonic functions. As I said, I said earlier that I will not get into the derivations. So if you wish, you can actually derive these relations. The derivations are available in complex analysis, advanced book like engineering, mathematical engineering books or something like that. So you can go through the derivations, but they are not really helpful for now. In solving problems, all you need to know are the important formulas. So this is what we are going to do here. Therefore, I have not derived, I have just given you the result, that what is the polar form of CR equations. So they are these. So we should remember both these CR relations, this one, this rectangular form, and the polar form of CR relations. So they are very helpful. Now, since we know these CR relations, now we are in the place to define the harmonic functions. So it says that if f of z is equal to u plus iv, and this to be analytic function, in let's define some region of the z plane. In some region of z plane, then we know that what are Cauchy-Riemann equations that this function is going to satisfy. They are this. So then So if the function f of z is analytic in some region of the z plane, then the CR equations are satisfied in that region, of course. And what are they? We have already written del u by del x equals del v by del y, and del u by del y equals minus del v by del x. Now if you differentiate this one more time, both the relations, and I will skip the calculations, but we will end up with, they're just very trivial, you can do that, you will end up with, okay, let's do it. Let's differentiate this whole equation with respect to x. This is a very little derivation, so better we go through it. So if we differentiate it once more with respect to x, then it will be del square u by del x square, and then this will be equal to del square v by del x del y. Similarly, if we integrate this with respect to y once again, then this will be del square u by del y square, and here minus del square v. Del x is already there, and we are differentiating with respect to y, so del y del x. Now we assume that del square v by del x del y is just equal to del square v by del y del x. So the order doesn't matter. The final answer should be just the same. This is what we are assuming. That whether you differentiate v first with respect to y and then with respect to x, and you get some result, then you do another process that you differentiate v first with respect to x and then with respect to y, and you get the result. And both of these the result of at the end of both this process should be the same. So that is what we mean to say here, that what we are assuming is that we are differentiating v with respect to x and y. So we are differentiating v 2 times, but then either way you can differentiate, order doesn't matter. First you differentiate with y or x, doesn't matter. Finally you are going to get the same result. If this is true, then you can say that in both this equation these terms are just equal. So if you just add them up, if you add this equation 1 and 2, then we will have del square u by del x square plus del square u by del y square, and on the other side what did we have? We had this minus this, just the order are different. So we had del square v over del x del y minus del square v over del y del x, and we said that both of them are just equal. That means this will cancel out too, and this will lead to 0. So the final answer is del square u by del x square plus del square u by del y square equals 0. And similarly we can achieve similar result for v, that del square v by del x square plus del square v by del y square equals 0. Okay, so I just derived it because it was a very little derivation, but again there is no need to go through the derivation. All you need to remember is this, because these are important results, and we can say that when we get this kind of results, then we can say that the function u satisfies Laplace's equation, because Laplace's equation is nothing but this del square u equals 0 and del square v equals 0. If you don't know this, then it's okay. You might, in case if you have studied vector calculus, then you might have come across this Laplace's equations and Poisson equations. But if you don't know, then do know this, that when you have this kind of structure, that you have a function and you take a double derivative of it with respect to x plus again the double derivative with respect to y, and if you get that equal to 0, then it is called the Laplace's equation. And since here u and v both satisfy the Laplace's equation in two variables, see, u satisfy Laplace's equation in two variables x and y, and similarly v also satisfies Laplace's equation in two variables x and y. X and y are our variables, so they satisfy the Laplace's equation in two variables, and therefore they are called harmonic function. So here the function u and v satisfy Laplace's equation in two variables. Two variables are x and y. Therefore, they are called, means u and v are called harmonic functions. Okay, u and v are called harmonic functions. Okay, why they are harmonic functions? Because they satisfy the Laplace's equation in two variables. Alright, then there is one more little result we want to know, and that is orthogonal system. Now we consider two families of curves. One we define as u of x y equals to c1. C1 is just some constant, and v of x y equals c2. Then we differentiate this first curve with respect to x. Then we will have del u by del x plus del u by del y, but then we want to differentiate it with respect to x, therefore it will be del y by del x again, y with respect to x, and then that will be del c1 by del x. But since this c1 is constant, so this will lead to 0. I hope this is clear to you. If you have any doubt in this, you please ask me in the group. In case if you have any difficulty, I will help, otherwise I will skip this for now, and I assume that you know this. So we have del u by del x plus del u by del y into del u by del x equals 0. Sorry, del y by del x equals 0. Okay. Now we make del y by del x as a subject, so del y by del x will be equal to, let's forget this for now, move this term to the other side, so we will have minus del u by del x, and then this will go to the denominator, so del u by del y. Okay, and then this, now we know from CR equations that del u by del x is nothing but del v by del y, and del u by del y is minus of del v by del x, but then that minus and this minus cancel out, and we will have a resultant positive sign. I call it M1. I call this relation M1. And similarly, you can get, so if you differentiate this second family, this v again with respect to x, and you go through the same process, then you will end up with del y by del x is equal to minus del v by del x upon del v by del y. I call it M2. Okay, and we just do multiplication of M1 and M2. Then you see here that what is M1? You see here what is m1? It is del v by del y whole divided by del v by del x. And then what is m2? It is minus del v by del x whole divided by del v by del y. So this is one whole term, this is also. So consider this whole bracket as a term. So you see that this will cancel out and this 2 will also cancel out. So we are left with minus 1. So the final result we get is m1 into m2 equals minus 1. And this says that u of xy equals c1 and v of xy equals c2 form an orthogonal system. And therefore this is something we should know, that every analytic function f of z equals u plus iv defines two families of curves u of xy equals c1 and v of xy equals c2, which form an orthogonal system. Okay, so whenever you have any analytic function f of z u plus iv, whenever you have such kind of function which is analytic, then you always have u of xy and v of xy, and so this is a family of curve c1. Okay, so u of xy is c1, it is defined as c1, curve c1, and this is c2, and both of them will form an orthogonal system. Any system is called orthogonal when this m1 and m2 is equal to minus 1, and we have derived it. Again, you don't need to get into the derivation, but you have to remember this result, that for each and every analytic function, u and v family of curve will always form orthogonal system. Okay, I don't think they are of much use while solving problem, but still it is important to note, at least we should know this, that u and v form orthogonal system. Okay.